Hello, this is the next video in a playlist that I'm calling Applied Multivariate Analysis. And we're in chapter 5 part of this playlist, which we're calling Comparing Population Mean Vectors. Let me jump to today's topic, which is one sample profile analyses. Now, this concept is so powerful and so useful in multivariate analysis. It really deserves more time than what I'm going to give it. But I think it's going to be a nice introduction, and then you can explore more of this on your own. Now, if y is a multivariate normal random variable, mean vector u, mu, covariance matrix sigma, and all the variables have to be measured on the same units and approximately equal variances. Not a total requirement there, just approximately. Now the goal is to compare the components of this mean vector, mu1 through mu p, and one basic hypothesis is that the profile is flat or level, meaning all the components are equal, or something's different, right? And that's a very vague hypothesis, and because it's so versatile, so powerful. So one set of hypotheses could be that the successive means are the same or are they different? Mu1 minus mu2, mu2 minus mu3, all the way to the pth component. Or you could compare each component with the first component. Mu1 minus mu2, mu1 minus mu3, mu1 minus mu-p. Are those all zero or is something different? And that's what this alternative is saying. Hey, they're not all equal. Something's different. And we can do this, we can express these hypotheses with the matrix C. So remember, we have a mean vector, mu1, 2, 3, 4, all the way down. And if we use this C times mu, then you can see that the first component minus the second component gives us this value. Then here's mu2 minus mu3 all the way down. And this matrix, if we call it C, we use it, then it's mu1 minus mu2, mu1 minus mu3, all the way down to mu1 minus mu-p, right? And these matrices are P minus 1 by P matrices, C. They're full row rank, and they're such that the rows add to zero. So remember, the little j is a vector of ones. And so you take a matrix times a vector of ones. It's adding the components. And here we're saying that each row adds to zero. And if you can see here, 1 minus 1 is 0. 1 minus 1 is 0 all the way across. And so then we can base the hypotheses on this transformation, C times mu. Is it 0 or is it, something different? Well, when each row in the matrix C is called a contrast. It sums to 0. Now these are pretty simple, where it's either 1 or minus 1, but it doesn't have to. It can have 2 and 3 and then minus 1, minus 1, minus 3. As long as they sum to 0, it's called a contrast. In both profile analysis of what we're doing here, these types of hypotheses, and contrast, they have a vast literature. And this is just a brief introduction. So to test this hypothesis is that this transformation 0 or it's not 0. We have a sample y1, y2, all the way to yn, and we transform each y by z, or 2z, to c times the vector y. The sample mean vector, the sample covariance of z are given by this, and the covariance matrix CS C prime. And when H naught is true, then this transformation C times the mean vector, it's 0. It's a multivariate normal, mean 0, and then this covariance matrix C sigma C prime, which is transpose, divided by n, because we're dealing with the sample mean. And we can use Hotel's t-squared. We calculate this Mahalanobis distance, and if it's too large, it's saying, hey, all these components are not 0, right? If the null is true, this vector should be all zeros. And if it's not, then we're going to get a big number. And if it's too big, greater than some critical value t-squared, then we reject and we say, hey, there's some component that's not 0. And of course, in my opinion, this is a better statistic. You're kind of getting that theme where we transform Hotel's t-squared multiply it times a constant, then it's an F distribution. And of course we can, we can back transform it and get the critical value, a t-squared critical value if needed. But this way, all programs have built-in F distributions, and so it's very easy to calculate, p-values, critical regions, etc. Let's go through some examples. Suppose we administer a drug to some subjects and measure a certain reaction time every 3 minutes. So mu1, 2, 3, 4, 5 designate the average response, between 0, 3, 6, 9, and 12 minutes. Now notice this. So each person, this is a repeated measurement study. So each person is administered drug, and then we look at the response every 3 minutes. So that vector is one person just repeated the same measurement each time. And that's fine. That creates a multivariate analysis. And so to test the hypothesis that there are no trends in the data, we could test this using this contrast matrix. Now notice that each row adds to 0. 1 minus 4, 6 minus 4, 1. Boom, it adds a 0. But this is specifically chosen. It's called an orthogonal polynomial contrast matrix. And it tests for linear relationships, quadratic, cubic, quartic trends, etc. And the R illustration will give this much more detail. This is just letting you know, hey, what's out there. We can test something like that. Here's another example where profile analysis. Oh, and this one, because it's a repeated measurements and we're looking at some sort of trend analysis, this is often called a growth curve analysis, but it's really profile analysis. It's all generically the same, but you might see it as a growth analysis. So suppose we're developing a combination product that reduces cholesterol and lowers systolic blood pressure at the same time. And, so we're adding a cholesterol reducing medication and a blood pressure reducing medication into one product. Now, to be FDA approved, that combination product has to be better than each individual product for these subjects that have high blood pressure and high cholesterol. So let's let mu1 be the mean vector that designates the average cholesterol and systolic blood pressure for the combination product. Mu2 is the mean vector for one of the individual products, and mu3 is the mean vector for the remaining individual product, right? Because these two products are combined together to be that combination product. Now, if we partition our response into Y, which Y1, Y2, and Y3. So, and realistically, Y1 is a random sample of patients that were randomized to the combination product. Y2 are the patients that were randomized to one of the single products, single drug products. Y3 is another population randomized to the remaining single drug product. Now, these are vectors, right? Y1 consists of cholesterol measurement and blood pressure measurement. Y2 is cholesterol and blood pressure, but for another group. Y3 is the same. Now, if we can consider them multivariate normal with mean vector here and covariance matrix sigma, then we can do a profile analysis on this, and I'll show you in a second. But notice that since it's a random sample, the samples between Y1 and Y2 and Y1 and Y3 are independent. And that's what these zeros mean. They're independent from one another. But there is a covariance structure within each population. Now, if we do some sort of matrix times Y, it's again multivariate normal. We covered that. And if we do C times the sample mean vector, it's also multivariate normal with mean and covariance matrix given by this. But now, to test the hypothesis that the combination product is different than the individual products, we could test this. Null hypothesis, C times mu is 0. With mu, of course, is the mean vector, but the contrast matrix is this. So this is the first component of population 1 times the mean of the first component of population 2. Are they the same? Then it's mean of population 1 times mean of population 2. So it's comparing cholesterol with the combination product against each single drug product. Then it does the systolic blood pressure times each of the other components. And we can test this. And what it does is it encompasses all the covariance structures associated with the two measurements. So this would be one way to test that. Let's do an R illustration. So Puthoff and Roy in 1964 reported measurements in a dental study on boys and girls from ages 8 to 14. And in our illustration, we're going to separate the boys. So I read the data from a data set from an FTP site, and there's 5 variables: gender, and then age 8, 10, 12, and 14. And here's sort of the first 6 rows, the head of our data matrix. We create a matrix C. Oh, I wish I would have printed it, but these are orthogonal polynomials that we're going to test to see if there's a linear trend, a quadratic trend, or a cubic trend in the data. Now, what this next step does is it isolates the min. So I create a vector of trues and false. And so when I subset the y vector, I want columns 2 through 5, which is just the data for min only, and I put it back in y. Now I plot the data so you can see this at age 8, 10, 12, and 14. You can see that it's pretty much a linear trend, right? So I'm hoping this test indicates that. So let's look what we did here. So I take the data matrix times C and store it in Z. And then I look at the column means and look at how big this linear trend is versus the quadratic or the cubic. I look at the covariance matrix as Z, and this is it. I want to know N and P. N is the sample size. Remember, it's the number of boys that we measured. I think is 16. P is the dimensions, which is 3. Mahalanobis distance is 77. You know, the test statistic, the hotelens t-squared. The critical region is 11. So we reject the null hypothesis. There is a trend in this data that we're detecting. Well, now we got to figure out what it is. So let's do tests on the individual components. So column 1 of Z tests the linear trend. So let's do a t-test on it. The p-value is really, really small. So the data says, hey, there's a linear trend. Well, then let's test the quadratic trend, which is in column 2 of Z. P-value is not significant, so there's not a quadratic trend. Cubic trend is in column 3, and it's not significant, so there's not a cubic trend. Okay, so 13 minutes. I went a little long in this video, but profile analysis and maybe growth curve analysis are so powerful and important that we had to cover it. So I hope you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.